Hello everyone, welcome back. In this video, we are going to start our discussion on k-nearest neighbors. And before we start the discussion, we're going to go through some vocabulary to understand different kinds of models and where k-nearest neighbors actually fall. So we're going to introduce another classification of models, parametric versus non-parametric models. So far, most of the models that we have seen are parametric models in the sense that we assume a functional form for the model and then we parameterize the functional form into some parameters which we can learn from the data, and then we use those parameters to construct this functional form, and then the functional form becomes our classifier. For example, we did logistic regression where the functional form is the logit function. We also have done linear models. Perceptron, the functional form is the linear model. SVM, we have different functional forms. We have, it could be a line, it could be more complex than that with the choice of the kernel. And all these functional forms have specific parameters that you need to learn along with them. And those parameters are learned from the data. They have the advantage of being simple. They are easy to estimate and interpret. And there's also a big disadvantage that comes with these functional forms is that the data, the real data, may not obey the assumed functional form. It may be different from the functional form that you chose, and many times it takes few iterations to get the functional form correct and working for the data in question. So that's why we try a bunch of models, we try a bunch of different kernels for an SVM, bunch of different neural networks with different configurations before we arrive at the right one for our data. And that's often how the course takes when we are using a parameterized functional form or a parametric model. There are also non-parametric models. Non-parametric models are data driven and there are relatively fewer assumptions made about the functional form, and we use data to make our classification. And the simplest model there is in this non-parametric section is called k-nearest neighbors. They're also called instance-based, memory-based, lazy models because we're not really constructing a classifier and we are only using the examples. So we don't do much work up front and we do most of the work at test time. So that's why they're called lazy. They're also called case-based reasoning models, kernel methods, and so on. Now, the nearest neighbor classifier. The nearest neighbor classifier has this very simple form where you match your test sample to existing data points based on some distance or proximity metric. For example, you want to classify a duck as a duck, then let's say we have some features that characterize a duck. If it walks like a duck, quacks like a duck, then it's probably a duck, right? So all these are features of a duck. And now in that feature space, we are going to plot the new data point that we have for the test sample. And then we are going to observe how near it is to different kinds of data points. Suppose we have other kinds of birds in our sample, we are going to compute the distance from each of these samples to our test sample, which is a duck. And then we are going to choose the k of the nearest data points. So we are going to choose whatever data points surround this data points and limit that to the number k. So the k is chosen such that we can make a comfortable classification, right? So k, we limit the number of samples that we select closer to the duck to be k. And out of these k samples, whichever category has the highest contributing number in this k is declared as the category for our test sample. For example, if there are number of ducks in this k, then our classification for this new test sample will be a duck. Now the learning algorithm is to just store the training examples. Because we are just using the examples at test time, we are not really constructing a model. There is really no learning happening at training time. At training time, our job here is simple, just store all the data points in the space. Just plot them, just store them. And then at prediction time, all the heavy lifting is done. At prediction time, to classify a new example, we find nearest examples to those examples. And then whichever class wins, let's say xi, yi correspond to all our nearby examples, and yi is the class of each of these examples, and whichever yi is occurring the most number of times is our prediction for our unknown class y for our example x. Now k nearest neighbor in action. So we have different values of k here. K is equal to 1 and k is equal to 5. For 1, we draw a circle around x only comprising of the first nearest neighbor. Now the first nearest neighbor here is a blue. Now if we choose k is equal to 1, our classification for this would be blue, right? And if we choose k equal to 5, then we draw a bigger circle around x to cover 5 nearest neighbors. Now we have 1 blue and 4 red data points when k is equal to 5. Now when we broaden this, our classification becomes red. Y is equal to red. Y is equal to blue for our data point x. Right? So you can see that the choice of k really matters. That really determines how accurate your classification is going to be. And common values that we use for k are up to 3, 5, some manageable number, because we don't want to go through all the training examples to determine the classification. That won't be accurate as well, because you have all examples in the space, and then we'll only classify every data point to be the one which has the highest number in the data set. Suppose we have 60 red and 40 blue, then everything would be classified as red, and that's not good, that's not accurate at all. So we only want to limit to the neighboring examples. Look at the neighborhood to make our classification. Now we are interested in decision boundaries in this course, right? We looked at decision boundary for decision tree. We also looked at the decision boundary for all the models that we have looked at after, right? Logistic regression, perceptrons, SVMs. The more complex the decision boundary, oftentimes better your prediction. But also some boundaries can be too complex for your data, so you always want to choose the right amount of complexity that is required for classifying your data. Now, KNNs have a very interesting decision boundary because we are using the data points themselves and not per se constructing a function or constructing a decision boundary. So our decision boundary for KNNs involves the data points, and we use the data points to construct this decision boundary. So if you can see here, it definitely looks like a beehive here with all these cuts and lines here, right? But it's actually much simpler if you pay attention. So if you consider, let's say, these 2 points, the decision boundary is simply a line that's equidistant from both these points. And that is this line. Right? And similarly, you can construct a line for these 2 points. And that would be this line. And so on. Right? So this line, all these lines are equidistant from one pair of points. So this blue line is equidistant from the points marked as blue. So these lines together form this complex decision boundary. So, and the boundary cuts here because in here we want, so now let's understand what the boundary actually signifies. So suppose you want to make a classification of this point. Then you will look at this data point, right? Suppose the point actually lies on the other side. Then you will look at this point. So that's exactly what the boundary signifies. And when 3 points are involved, then you need to look at this intersection right here and then see on which side the point lies, here or here or here. So that's why the boundary becomes complex when multiple points are involved. So this decision surface is called a Voronoi decision surface, and the classification follows this decision surface intrinsically. So just to understand how that the decisions are made, we want to understand this boundary and how this is constructed. All right, so the key idea behind instance-based learning is to store all the training examples. And then if you're going by one nearest neighbor, you locate the nearest example xn to the query example xq and estimate y to be equal to the same y for xn. Now for k nearest neighbors, we take a vote among k nearest neighbors if it is discrete valued. So can k nearest neighbors tackle continuous valued features? Yes. Then you take a mean of the values to estimate the y of the query instance. There are some modifications of KNN that have evolved. There are many of those. One of those which is very popular is to weight nearer neighbors heavily than ones that are farther away. So it makes sense, right? So we want to consider as many examples as possible because we don't want to limit ourselves to 5 or 10 and then lose something that a farther away example could contribute to our prediction problem. and we want to take that into account. But at the same time, we want that don't want that to influence our prediction too much. So we want to limit its influence. To do that, we can weight each example by the distance, and then where the weight would be 1 by the distance square of the distance. So this is the weight. So which means that as it's farther away, it would contribute lesser. When it's closer, it would contribute more. It's an inverse of the distance, right? And then weight that to the y value, y or f of xi, which is the prediction of each xi data point, and then that weighted value would be used to determine the y value for our query instance xq. Now, in the distance weighted KNN, we can still limit our number of k to 10, or maybe we can increase it now to 100 or so. We can also use all the instances instead of just k. So that's called the Shepherd's method. It's called the Shepherd's method if we use all the training examples. But we can typically use a greater value of k without really hurting the performance of our test at test time. So now this is definitely computationally more expensive, and KNNs in general are computationally more expensive because all the work, all the heavy lifting is done at test time. And if we are doing distance weighted KNN, it would be even slightly more computationally expensive because we are looking at a higher value of k, or maybe potentially all examples. So keep that in mind and weigh the trade-off between computational requirement and also your performance gains, and that would help us in determining the right value of k. So there is definitely a trade-off between these two things here, right? So you should keep that in mind when you pick and design a KNN for a problem. All right, to sum up, KNNs can be considered when there are lots of training data, but still manageable. Not too large a training data set that it's really expensive to even store all of them in memory. And less than 20 attributes per instance. Now, this is like a ballpark number for you to understand when to consider KNNs. If there are too many attributes, then the space where you plot your data points becomes too huge, right? So 20 attributes per instance means that the data is 20 dimensional, right? Now, if you consider even more attributes, some of the biology datasets have 10,000 attributes. Vision datasets sometimes can have lots of attributes, and those can have a huge impact on your performance. And not just performance, KNNs may not really work well because just the space is too large that even near the concept of near loses its significance. Even near is too far to be useful. So, like for example, our universe, right? We have lots of these of stars and planets far away, where the nearest itself can be really far away. The next nearest star is pretty far away, right? So that is something that would happen with KNNs. If you have too many instances, then it's not really clear if near means something. And that's why we limit the attributes to around 20. The advantages are also there. KNNs have been used in the past. They've been used for simple image classification tasks, and they've actually seen quite a bit of benefit there. Training is very fast. Actually, there is no training. That's why it's very fast. It can learn complex target functions without really coming up with a functional form. So that is where KNNs really shine. You don't need to come up with a functional form. And even without coming up with a functional form, you can construct complex functions. For example, we saw the Voronoi diagram, right? Voronoi is a really complex decision space. And you did not come up with that. The algorithm, the nearest neighbor algorithm, can automatically use that to classify. But if you are using SVMs or let's say SVMs, for example, then we have to find a really complex function which can map our data points to that high dimensional feature space to be able to do such a complex functional form. And that's really where KNNs shine, because you don't need that functional form, but you can still do complex target functions. And they don't lose information. Oftentimes, all the data points are not really used well enough in classification, and that is something KNNs really shine. Because, for example, in SVMs, we use the support vectors more than others to aid in our margin, construction of the margin. But in nearest neighbors, the data points can occur at multiple places in our space, and still we'll be able to look at the neighbors of that data point in that neighborhood to make a classification. And it's also robust to noise in that we are considering 5 or 10 examples, and if there are a couple of noisy ones, it may not really matter in the classification. Whereas some models are really sensitive to noise. For example, even SVMs, if there is noise near the support vectors, outliers near there, then the margin may shift and may lead to a really poor classifier, which at test time does not generalize well. And there are also many disadvantages. It's slow at query time, that we know, because it's not learning anything, it's using the stored examples at test time. And it's also easily fooled by irrelevant attributes. And this is something that occurs more commonly than other disadvantages. Query time, yeah, of course it is slow, but it's still a good model. We could use it, but there could be attributes which are not really helpful in our prediction problem. And those attributes can be easily filtered out if we have a functional form. Remember, we had L1 regularization, which could drive these features to 0, right? So L1 is also used for feature selection, and L1 regularization is easy to add to any loss function that we have for neural networks, for SVMs, logistic regression. We could easily add that, add L1 regularization to the functional form. But here we don't have a functional form, and hence all these attributes are used to plot the data points, and then in that space we want to perform the classification. And if there is an attribute that does not help in your prediction problem but still exists, and your KNN is going to use that and predict poorly at test time, and those attributes which don't really contribute are harder to detect and avoid in KNNs. All right, so that's introduces KNNs. We'll continue in the next video. Thank you very much.